Welcome to this explainer. We're diving straight into one of the most incredible scientific puzzles in history. Have you ever just looked at two everyday objects sitting on a table and wondered, hey, are those things actively pulling on each other? Well, today we're unpacking a total masterpiece of experimental design from the late 1700s. It's an experiment that managed to measure the seemingly unmeasurable. We're talking about the legendary Cavendish experiment, a setup so brilliantly clever that it fundamentally shifted our understanding of the whole universe. So that brings us to the core scientific question at hand. Look, we all know gravity pulls everything toward Earth, right? That's why things fall when you drop them. But the real mystery we're exploring today is whether we can actually measure the gravitational pull between ordinary, everyday objects sitting right inside a lab. Think about it. Is the attraction between two heavy metal balls on a workbench something we can physically isolate from the overwhelming downward pull of the entire planet beneath them? It's just a staggering problem of scale. And the crucial point here is that early scientists literally thought this was a fool's errand. I mean, they firmly believed the gravity between small masses was just way too incredibly weak to ever be detected by human instruments. You've got the force of the entire Earth pulling down, which completely overpowers any delicate, tiny horizontal pull between two objects on a table. Because of that massive interference, people thought it was absolutely impossible to measure. But then, a scientist named Henry Cavendish came along and proved them all wrong.
His genius solution? A little device known as a torsion balance. Instead of trying to measure objects pulling downward, which, let's face it, would just instantly get lost in the Earth's massive gravity, Cavendish designed a system to measure a delicate horizontal pull. By suspending the weights from above, he completely removed the Earth's downward interference from the whole equation. It's just a stunningly elegant mechanical workaround. It isolates those incredibly weak horizontal forces we actually want to observe, completely bypassing the noise of the planet getting in the way.
Okay, so let's get into how this mechanism actually works, because it relies on absolute delicacy. Cavendish took two small lead spheres and suspended them on the ends of a horizontal rod, which was hung by a single, incredibly thin wire. This setup allowed the rod to rotate freely on a horizontal plane. Then he brought two massive lead spheres near the smaller ones, and their tiny gravitational attraction went to work. The smaller spheres were pulled horizontally, causing that central wire to twist. And here's the truly fascinating part. As the wire twists, it creates a subtle restoring force. It's essentially fighting back against the gravity. Once those two forces, the physical twist and the gravitational pull, balance each other out, the system reaches equilibrium and stops moving. By measuring the exact angle of that microscopic twist right at the point of equilibrium, boom, you can calculate the actual physical force of gravity between those spheres. Now, you're probably wondering, how on earth do you measure a twist so microscopic that a standard scale can't even register it? Well, the real genius of this experiment lies in optical amplification. Cavendish attached a tiny mirror directly to that twisting fiber and bounced a light beam off of it, creating a massive, readable scale. So as the fiber twists even a fraction of a millimeter, the angle of the mirror changes, and that reflected light beam sweeps across a distant ruler in the room. Just like that, a microscopic physical twist is instantly amplified into a clearly visible, measurable movement. It is a wildly creative solution to an otherwise totally impossible problem. And once you can actually measure that twist, you unlock the underlying physics of, well, everything. Because the physical twisting torque of the wire perfectly equaled the gravitational torque pulling those spheres together, Cavendish was able to use Sir Isaac Newton's famous law of gravitation to solve for the missing piece. He just plugged his highly precise physical measurements into the formula, where force equals g times the two masses divided by the distance squared. By doing this, Cavendish didn't just measure some tiny localized force. He became the very first person to finally calculate big G, the universal gravitational constant. And this is where a simple tabletop experiment becomes truly earth-shattering. This constant, big G, is the exact same fundamental mathematical rule governing those little lead spheres in a laboratory as it is for the immense cosmic pull keeping the moon in orbit around the Earth. Cavendish's setup proved the strict universality of Newton's laws. Finding this exact constant actually allowed scientists to finally calculate the total mass of our planet, which is exactly why this astonishing feat is famously referred to as weighing the Earth. To truly wrap your head around why this was considered an impossible experiment for so long, we just have to look at the modern value of G. It's 6.674 times 10 to the negative 11th power. That is an unimaginably tiny fraction with 11 decimal places before you even hit the first actual number. We're talking 0.000. Well, you get the idea. It's tiny.
This incredibly small number proves exactly why scientists thought everyday gravity was an entirely lost cause. The gravitational force between everyday objects is practically zero, yet Cavendish managed to isolate, amplify, and measure it anyway. It's just wild.
Now, as we start to wrap things up, it is absolutely essential to separate the two different G's in physics, because let's be honest, they get confused all the time. First, we have big G, the immutable universal constant of nature we just talked about solving for. That is the exact same number everywhere in the universe, governing how mass interacts with mass. Then we have little g, which stands for the local gravitational acceleration. Little g completely changes depending on what planet you're standing on, how massive that planet is, and how far you are from its center. So big G is an unbreakable rule of the universe, while little g is just your local condition. Keeping that crucial difference in mind, I want to leave you with a final thought experiment to really test what we've covered today. Imagine you packed up Cavendish's entire torsion balance, the mirror, the light beam, those exact same lead spheres, and you set the whole thing up on the surface of the moon. Now, we know the moon's local gravity, its little g, is only about 1/6 of the Earth's. So here's the question. Would the actual horizontal gravitational force pulling those lead spheres toward each other change? Think really carefully about the difference between the universal constant, big G, and the local gravitational acceleration, little g. It's a fascinating brain teaser that proves just how profound Cavendish's experiment really was. Thanks for joining me on this explainer, and remember to keep questioning the universe around you.